Hello and welcome to this SCION Instruments webinar. My name is James Hogan and I'm the Applications and Lab Manager here at SCION. Today's topic will be FAME or Fatty Acid Methyl Ester analysis in olive oil using gas chromatography mass spec. We'll focus on things such as what FAMEs are, why we test for them, including some of the regulations surrounding it, and we'll focus on how we test for FAMEs, so some of the crucial instrument parameters on the GC and the MS that are needed for successful testing. So the first topic we're going to cover is what are we testing? What are FAMEs? So FAMEs, or fatty acid methyl esters, are formed by the esterification of a fatty acid with an alcohol in the presence of a catalyst. FAMEs can be produced from sources such as vegetable oils and animal fats, and FAMEs are found in many everyday products due to their strong solubility and lubricity such as cleaner, lubricants and fuels. So now we're going to take a look at why do we test for FAMEs in olive oil. So the short answer is quality control. So the analysis of FAMEs can determine the quality of extra virgin olive oil, or EVOs. Natural EVO is made by pressing or centrifuging olives without exposing the olives to chemicals or heat. Adulteration of olive oil is seen as it reduces production costs to mix the olive oil with cheaper oils such as sunflower or refined olive oils. The identification of a divergent fatty acid content in the product can indicate that the product is not natural olive oil, that it has been adulterated in some way. So now just to quickly highlight some of the regulations that are involved with testing extra virgin olive oils for FAME content. So regulations from bodies such as the European Union and the International Olive Council, the IOC, are in place to define what classes as an olive oil, as well as defining safety and quality standards that are to be followed. So, for example, the International Olive Oil Council states the fatty acid composition of olive oils which determine acceptable purity standards, and this can be seen here in this table on the right-hand side. Also, the Official Journal of the European Union states that extra virgin olive oil content of FAME should be less than or greater to 75 milligrams per kilogram. So these are examples of some of the regulations that need to be followed and as why we would conduct tests on olive oil for fatty acid methyl ester content. So we know what we're testing, we know why we're doing it. Now we're going to look at how we can test for fatty acid methyl esters. So for this application, a commercially available FAME standard was purchased. This contained 37 FAME compounds in a pre-made mixture with concentrations ranging from 150 to 600 microgram per mil. This standard was used for the qualification and then subsequent quantification of the unknown olive oil sample. The FAME standard was used to create a calibration set in the concentration range of 0.2 to 50 microgram per mil. We also decided to employ an internal standard to help with the reproducibility of our results, and we chose to use one of the deuterated versions of a FAME compound, so deuterated methyl heptadecanoate. This was employed at a concentration of 50 microgram per mil. For more information on internal standards and on analytical standards in general and their uses in qualitative and quantitative analysis, you can find several technical notes on our website. So I just wanted to quickly illustrate the FAME standard here and its content. So this has been replicated from the certificate of analysis that was provided with the standard, and it shows the 37 compounds that we used to characterize the olive oil samples, and the concentrations of each of these FAME compounds. So over the next few slides, we're just going to focus on some of the key method parameters that were employed to test for FAMEs in olive oil samples. So we're going to focus on some of the GC parameters, so the injection technique that was employed, the choice of column, and then the oven ramp also. On the MS parameters side, we'll focus mainly on the scan type, so SIM or selective ion monitoring, and why that's important. We'll take a look at the internal standard and why we employed that, and then we'll also take a look at the method validation, so ensuring that our method is working well, and we'll talk through the linearity, precision, and then also recovery spiked samples and why they're so important. So the GC parameters are really important, as this is what allows you to achieve the desired resolution and separation for your target compounds. So for this application, we decided to use the application-specific SCION FAME column, and we employed a very slow oven ramp. So these two things combined allowed us to achieve the best separation of the cis and trans isomers for the FAME compounds, which is so crucial for olive oil analysis, as we're able to detect whether it's been adulterated in some way by the comparison between cis and trans. The FAME analysis can also be performed on other columns, such as the SCION wax, but we will lose some of the resolution between cis and trans. So it really depends on the required characterization of your samples and of the FAME compounds as to which column you will choose for your analysis. Another thing to focus on was our liner choice. So we chose one of our focus type liners. So this is a base deactivated liner, which helps prevent active sites, and so will lead to less tailing and ill effects of our standards, and will help preserve the analysis. Just one thing to mention before we move on, we do have liner and column selection guides on our website, so you can see those for more information and to help guide you on your choice. So the next thing we're going to focus on is the mass spec parameters. So first of all, we're going to talk about the ionization mode. So the ionization technique used in this application was electron ionization, or EI. So electrons from the filament ionize the gas phase molecules into ions and fragments. The reflector behind the filament ensures the ions are then traveling in the correct direction, where they are accelerated towards the quads using the repeller and focused by the lenses. Electron ionization, or EI, is regarded as a hard ionization technique, which causes significant fragmentation of sample molecules. So the most important aspect of this analysis that we used was the scan type. So we use something called selective ion monitoring, or SIM mode. So this is when the MS will only search for pre-selected ions. So SIM mode is 5 to 50 times more sensitive than full scan mode, and works by using selected quantifier and qualifier ions for a known compound. Quantifier ions are used to quantify the compound, and it's typically the most abundant ion in the mass spectrum. And then the qualifier ions are then used to help confirm that you have the correct compound, as they have a known ratio to the quantifier ion. So typically you will have 2 qualifier ions, and these will be the 2 next most abundant after your quantifier ion for each compound. And our MS Workstation software will automatically select these for you when you're building a method, and you can find our method development guides on the website as well. We have here a picture example of a TIC, or total ion chromatogram, and this is just showing the separation of all the 37 FAME compounds that were being analysed in this application. So an incredibly important step for FAME analysis in general and FAME analysis in extra virgin olive oils is the sample preparation. So there are some procedures already set down. So for example, the Official Journal of the European Union provides a procedure for FAME analysis in olive oil, and this is what we followed during this application. So to prepare the EVO sample, 0.1 gram of the olive oil is transferred into a test tube. To this tube, 5 ml of heptane is then added. We changed this ever so slightly, so we added 250 microliters of our internal standard working solution, and then made the volume up to 5 ml with heptane. So we added the internal standard at this point so that we could help to track any variations throughout the sample preparation steps, and then also when introducing it to the instrument. So this will help with our reproducibility of our results. Once we'd added the heptane, we mix it, we shake it briefly. We then add 200 microliters of 2 molar potassium hydroxide solution dissolved in methanol. So this is added to perform the esterification process. And we do this by, once we've added the solution, we then shake it vigorously for 30 seconds, and this should ensure that any of the fatty acids are esterified into FAME compounds. The solution is then left to stratify until the upper layer of the solution becomes clear. This upper layer is then transferred into a GC sample vial and is now ready for injection on our instrument. So over the next few slides, we're going to take a look at some of the results that we obtained from our analysis. So we'll start with looking at the mass spectra and how we use the NIST library to confirm the identity of each of our components in our standards. We'll look at the resolution from the FAME column, and we'll take a look at some of the reports that were generated from our mass spec workstation software, and take a look at some of the results from the method validation as well. So this slide is just to highlight sort of how we built our method, basically. So here we can see 2 mass spectra from 2 different FAME compounds. So this was taken in full scan. So we scanned from a set mass range, so from I believe 30 to 400. And then the two pictures here on the right, so the top one where we see the red, this was the spectra for dodecanoic acid methyl ester, so taken from the standard, from the injection. And then we have the corresponding library match underneath that. And then same again for the one below, we have octanoic acid methyl ester, the standard spectra in red there, and then the corresponding NIST library match spectra. So from this, we were then able to build our SIM method. So we would take the most abundant ion of each compound as our quantifier, and then the two next ions as our qualifiers. So the important thing about this is that a lot of the FAME compounds share a lot of the same fragment ions, but the fragmentation patterns may differ. So this is where the library search is so important, as it enabled us to confirm which compounds came in which order, and then we were able to build a SIM method with the relevant quantifier and qualifiers with the right mass ratio to help prevent any false positives. So here we can see an expanded TIC or total ion chromatogram. So this is just to illustrate the effectiveness of using the application-specific FAME column. So we can see here that we have really clear separation between the cis and trans isomers, which is so important for FAME analysis in olive oils. So this is going to enable us to clearly see if there's been any adulteration, and then we can follow the regulations and guidance on the amounts of each compound. So here we have an example of a report type that can be generated from Mass Spec Workstation. So there are a number of predetermined, preset report styles that can be used, as well as a more customizable reporting template that can be employed. So here we've decided to use one of the predetermined report templates, and we can see examples from two compounds here from an analytical standard. So we have methyl oleate and methyl linaloate. So within this report, we've determined pass and fail criteria for things such as retention time. We've decided that that needs to be within a certain time scale, and also for the ion ratios between the quantifier and the qualifier ions. So this allows us to very quickly see whether we've got the correct compounds, whether all the predetermined pass-fail criteria have indeed passed, and then it also gives us the peak area and the amount calculated within the software. So it allows us to review very quickly. So on this slide we have some example results from the method validation that we conducted while undergoing this analysis. So we can see here some example of the linearity results. So for all compounds, the linearity results were obtained at 0.99 or higher. So this is an excellent result, as many regulations will require a value of greater than or equal to 0.98, for example. The precision of the method was also obtained by 7 consecutive injections of a mid-level FAME standard, which contained a range of compounds from 10 to 25 microgram per mil of all FAME compounds. The repeatability results show the majority of FAME compounds were well below 1%, with all of them well below 2%, which is often an acceptable criteria of method. So that showed that there was good system precision and that our method was working well. We're happy with the method, and then we're able to analyze olive oil samples. So on the table on the right there, we have some examples, limit of detection and limit of quantifications. These were theoretical, these were calculated, and then we also have some amount found in sample, so of some of the compounds found. If you take a look at our application note on the website, you'll be able to see in much greater detail the results and the interpretation of the results also. So we were then able to compare the composition of identified FAMEs from the EVO sample and compare with the specifications. So from the amounts on the previous page, the microgram per mil, we were able to convert this into the percent found in the sample using the mass of the olive oil, and then we could compare this with the specification range. So only one of the 7 FAME compounds that were found within this sample is above specifications. This was methyl palmitate. So when an EVO is suspected to be adulterated, it mostly results in divergent methyl oleate or methyl linaloate content, but not methyl palmitate. So another confirmation that the EVO is not adulterated is to check the presence of trans isomers. So this analysed EVO, extra virgin olive oil, did not contain any trans FAME compounds. So This should basically indicates that the sample was not exposed to any heating process or any adulterations and is likely an authentic EVO. So just to wrap up this webinar, I'm going to spend some time covering some of the features and highlights of the SCION 8700 SQ. So here you can see an overview of the inside of RMS. So first you can see the transfer line with the column coming from the GC, then into the source, then Q0, Q1, and then finally the detector at the end. So some of the benefits of the SCION MS. So it's lens-free ion path. So this can increase sensitivity by reducing ion losses, leading to more accurate quantification and identification. We have a curved Q0, so the multi-curve design, the 90 degrees curves Q0 and the 90 degree off-axis axial detector. This reduces the neutral noise, so anything that isn't ionized will simply pass through the source, as you can see with this yellow arrow here, and not follow the red ion path. So we will lose any of the neutral species, and only ionize the things that we're interested in. The things that are ionized will pass through the ion path. This will help improve our signal to noise and give us a higher sensitivity. We have our extended dynamic range, or EDR. So this enables optimal detection in every scan, so we can accommodate both trace components and high abundance compounds in the same run. We have a high capacity turbo pump, 400 litres per second. This can means we have a very quick pump down speed and can help reduce instrument downtime. We also have a premium option, which comes with Q0 helium focusing that can increase sensitivity, and also has the option for EI and CI, chemical ionization mode. So finally, just to conclude this webinar. So to conclude, we were able to see good resolution between our cis and trans fame isomers using the application-specific SCION fame column. We were able to verify that there were no trans fame isomers present in an extra virgin olive oil sample, and therefore we were able to deduce that this hadn't been adulterated in any way and was an authentic EVO. Thank you very much for listening to this webinar, and please get in contact with SCION if you have any questions. Thanks very much.